So the answer is that it's true. Well, it better be true, because otherwise why have we been calling this a rank K approximation? And this is the key insight. If you have two subspaces of Rm, and S is a subspace of T, then the dimension of S has to be less than or equal to the dimension of T. And here, T is the column space of U, and S is the column space of U times V transpose. U has K columns, and therefore has rank at most K, and therefore the column space of U has dimension at most K. So if we can show that S is a subset of T, then we know that the column space of UV transpose has dimension at most K, and therefore U times V transpose has rank at most K. And that's summarized right here. How do you show that one set is a subset of another set? Well, you pick an arbitrary vector in the set that is the subset. So you pick Y to be in the column space of U times V transpose. And what we need to show is that Y is now also in the column space of U. Take Y to be in the column space of UV transpose. You then know that there is some vector X such that Y can be written as UV transpose times the vector X. So that gives you this result right here. But if you then take this to be your vector Z, then you know that Y can be written as U times some vector Z. But that means that Y is a linear combination of the columns of U, and therefore Y must be in the column space of U. So in summary, well, low rank approximation has broad application, and we showed how low rank approximation in a very naive way can be applied to data compression. A question now is, what is the best low rank approximation of a matrix? Because if A is equal to some U times V transpose, where this is the approximation, it would be great to take U to be the best K columns and V to be the best K columns, so that U times V transpose is the best approximation for A. Now the answer to that is related to the singular value decomposition, which is a much more advanced topic. We will touch upon what the singular value decomposition is at the end of this week. For now, you're just going to have to live in suspense.